Hey, what's going on? Welcome to yet another AltDevBlog video, because I don't feel like writing things, like making complicated animations is any easier. Alright, so who am I, and why am I qualified to talk about this? My name is Jamin Kessler, and I'm not. I'm going to go ahead and blame this on the Codeplay guys. They have some of the absolutely most brilliant people in the industry doing compiler tech, and they're not making videos about compilers. And if they don't want to make the videos that I want to see, then someone has to do it, and it might as well be me. So, yeah, to you Codeplay guys, if you don't start making videos, I will continue to put out boring, uninteresting, and possibly misguided and factually incorrect videos about compiler techniques. So you might want to get on that as soon as possible. Okay, so this is going to be about register allocation and what's involved in it. It actually has some implications, and it's good to know when you're doing optimization, just some stuff to keep in mind, but we'll talk about that later. Moving along. Okay, so here's a crappy example that I came up with. On the left is memory. Memory obviously has addresses, and I've listed the address and the fake value that happens to be stored there that I just made up right now. That big blue box in the middle is supposed to be something CPU related, but on a real CPU, registers do not take up 33% of it, and the stuff that's blank has other useful things like execution units and cache. So I'm going to walk you through, number one, what registers are, and give you a short assembly program to basically illustrate how they're typically used. Okay, so here's a fairly normal bit of C code. You're quote-unquote storing 33 in X, and you have you're setting Y equal to 44, and then you're doing an operation involving X and Y and storing the result in Z. So when you actually do stuff like this, you cannot operate directly on values in memory because most CPUs don't have instructions that can operate on things in memory. We'll get into that in a bit. So what you have to use is registers. They could be for storing integer-like things, floating point values, vectors. You know, there's different register sets for different things. Some overlap and are aliased. Some registers are just unified, and you can store a float or an int or whatever you want in them, like on the SPUs. So hopefully the assembly will make it a little bit more clear. Hot. I probably shouldn't have said that. Okay, so this is what some fake assembly might look like for the program that you see above. So we're going to go ahead and pretend that the variable x that you see up there is stored in address 8, and the variable y is stored in address 2c. Now, if you look at the memory on the left, if you look at address 8, it really has 33 in it, and if you look at address 2c, it has 44. So everything kind of matches up. So first thing we're going to do is we're going to take what's at address 8, and we're going to load whatever value is stored there into register R5. So now, as you can see, register R5 now contains the value 33. We're going to do the same thing for whatever happens to be stored at 2C, which looks like it might be 44. Okay, going to load 44 in. Now we're going to take the value that's currently in register R5 and in R9, we're going to add them together and store the result in R6. It's destination source source for the registers here. So add those together and get what I hope is 77, but it may not be because I kind of suck at arithmetic. And then we're going to take the value we just wrote into register R6, and we're going to store it back out to memory in address 24, which is where I guess Z might be located in this fake example. Okay, there you go. So that's basically how things are done. So now here's a little bit about the why. Okay, so why use registers at all? I mean, it just seems like you're doing a lot of unnecessary copies, and you know, why even bother? Okay, so number one, you have a lot of RAM in your system. Well, a relatively large amount of RAM in the system, but reading to it and writing from it is agonizingly slow, even with cache. Number two, while you have a very, very small register set, I mean, some CPUs have 16 general purpose registers, some have 128. I mean, it varies, but it's still very small. But the value that's in there can be used immediately. And what I mean by that is that you don't have to load it in from memory. It's just you can pretty much and I know this is a stretch here and this is slightly inaccurate, you could pretty much operate using CPU instructions, directly on stuff in registers. In actuality, you have to fetch things from registers, and that can take time, and you can only fetch from so many registers per cycle, but in general, it's almost immediate. Another thing is, in that last example, we didn't really do anything interesting. We calculated a value into Z and then we stored it out. In the real world, you're going to want to take this value that you calculated and you're going to want to use it over and over and over again in lots of different things in the code. So it helps to keep it in registers, because if you run out of registers, you have to start taking things that are in registers, temporarily storing them out to memory so that you can free up registers, and then when you need that value again, loading it back in, and that takes mad time. Like I said before, not all ALU operations can operate directly on memory, so you can't say add the thing at address 5 and add the thing at address 27. Number one, because they're not aligned, but mainly because there are no instructions to do that. You have to operate on things that are in registers, so you want the things that you use to be there and to stay there if possible. And finally, because people who write register allocators would be unemployed, and that's bad for the economy. I'm looking at you, Pete. Okay, so here's a little bit more complicated example, and this is sort of deliberately concocted to introduce a couple keywords that we'll need for the next slide or two. So let's look at int x equals 33. So here's the variable x. We're going to assume for this example, and there's nothing on this slide that would tell you this, I'm just making this up, that value is located at address 8, and we're going to load it into R5 because that's what the compiler happened to assign to it when it did that. Okay, so that first instance where we're loading into R5, you could sort of think of it as a definition. Like you're not defining a new variable, but you're calculating a new value, or you're loading a new value and you're sticking it in R5 for the first time. That's a definition. The two green boxes below that are your uses. You're using R5 in that add instruction, and then you're using R5 again in that sub instruction. So you have your definition and you have your use. Okay, let's take a look at why. Okay, sorry, actually this is the range that R5 is needed from. So basically where that green bar is, it starts with the load R5 and it ends with the very, very last time we use it. In the time in between that bar, we cannot use R5 for anything else because the add and the sub need that proper value to be in there to get the right result. So now we'll look at y, I hope. Okay, y equals 44. Assume it's in 2C, like the example before, and we happen to be storing it in register R9. This is our definition of the thing, the little semantic thing that is in R9 now. And those are our uses. So we're using it in the add and we're using it in the sub. And this is the range that it needs to be live in. From the time that we define it until its last use, we can't change that value because we need that value to calculate stuff. And then, so now here's an interesting one. We're not loading anything in, but we're taking a bunch of numbers, we're adding it, and we're storing the result in R6. Again, this is a definition. This is where the thing in R6 is being set and is being sort of defined. And then down here we have our use. Now, let's show the range. Okay, now it's a little weird that that second to last instruction uses R6 and then writes to it. In this case, the R6 that is currently highlighted in blue is the final use of that thing that we calculated during the add. But then we're going to take the result and write it back into R6, which now we're defining something else. From this point on, R6 is something entirely different than it was before. Then we're going to store it out. And the range that this thing needs to stay alive is, we're going to call it R6 prime. And it's that. Now, I'm doing things kind of backwards because I want to show you how you get to the point where you assign registers, but to show you live ranges and def use with registers already defined is a little bit confusing. So it's a little bit out of order, but that's the way I happen to do it. Okay, so now that you know what a definition is and you know what a use is, I want to talk a little bit about def use webs. Now this example was sort of borrowed from MIT, so I must give them credit. It's an excellent example, and the video that I got it from was kind of low quality, so you could barely see what was being highlighted. Hopefully this is a little bit more visible. So yeah, I just wanted to give credit for this. I did not make this example up. So look at the top right, you have def y. So we're defining y, and then down there is where we're using y. So this thing is a web. We're basically defining it, and then all the uses are in the same web as the thing you defined. So what else is a web? Obviously this one. Here we're defining x, and then we're using that x. So those two things are in the same web. We'll go to another simple one. Okay, down here, you have def y and then use y in the same web. And then finally, this one is a little bit more complicated. Don't freak out. Just calm down. Prepare yourself for what you're about to see. It's pretty big, right? Okay, that's what she said. So here we have a def x. We're talking about the one on the right-hand side. And then a little bit to the left and down, you have use x. So they're kind of in the same web because you're defining x and using x. Same thing with the one up and a bit to the left. You have a def x and then a use x down there. So this whole big thing is just sort of one big web because they can all kind of see each other, the definitions and the uses. So these webs are going to be our unit of register allocation, and we'll see why in a second.